So this is question number 20. A solid cylinder of mass, radius r and length L, falling concentrically through a vertical tube of radius r plus delta r, where delta r is much smaller compared to r. The tube is filled with gas of viscosity mu and mean free path L. Neglect fluid forces on the front and back face of the cylinder and consider only shear stress in the annular region. Assuming a linear velocity profile, find an analytical expression for the terminal velocity of fall V. Terminal velocity of fall V of the cylinder for no slip and with slip. So for slip condition, okay, what is the idea of this one? So it is about you have a cylinder here, and then you put this cylinder into a hollow cylinder like this. So and then it's depend. We have a fluid here. So fluid means it may be liquid, it may be gas. So and for sure this object is falling due to the weight. So means that if you have a fluid here, whether it is gas or liquid, so this fluid will resist the movement. So here actually this is the idea to measure the viscosity of gas or sometimes viscosity of cylinder. So means that if the viscosity is higher, means that this object will take a lot of time, more time to falling down. Okay, so and then we are calculating. So viscosity is actually very near to the shear stress. That's why when we calculate viscosity, we are using the idea of shear stress. Okay, from where the resistance comes in. So we focus on this wall. So means that we have a cylinder wall and this is the hollow cylinder. So and then the molecule here stick together, stick very hard on the surface. That's why in this situation we have slip, with no slip condition and with slip condition. So for no slip condition, normally it will create a velocity profile like this one. So and then because there are shear stress here, the no slip condition is actually caused by shear stress. Okay, so because of the shear stress here, so it will slow down the object, and then the resistance comes in. That's why in this question they ask you to consider only shear stress in the annular region. Okay, and then we need to neglect the fluid force on the front and back faces, because if we have this one, so the cylinder of this one is actually will give resistance when these objects falling down. Okay, so that's it, the idea of this situation. Okay, I think you are familiar with this one. And then if we go, so for no slip condition, we know that shear stress is equal mu du dy. So and then we substitute because it is given that the velocity is v and the dy is delta r. So as I said, so we have a cylinder here falling down. So it is clearly say that the object is falling down with v. So we change the du as v. Okay, why? Du is normally the difference of velocity, but the terminal velocity means the velocity is now become constant due to the the weight limited of the mass. Okay, so in previous calculation I also explained about the terminal velocity. So when you're falling down at certain time, the acceleration is almost zero because the velocity is keep remain its value. So du means the changes of u, but we replace with the value of v because it reached the terminal velocity. And the dy here is actually the gap between two moving plates. So in this situation, the two moving plate is actually this plate and this plate. this surface and this surface. So means that the difference of this one is actually delta R, because okay, this is the radius of the falling cylinder, and this is the idea of R plus dr. So you need to understand about this one, R plus dr. So means the gap between the cylinder and the hollow cylinder is very small. So means that the dy is now delta R. Okay, so and then we in equilibrium, so means that in one split second free body diagram, we assume that the weight is equal to the tau A. So it's very simple. So we have a cylinder here. So we have a weight come down, mg, and then the resistance here caused by the tau times A. So it is mg is equal to tau A. So we substitute the value of here, the tau is mu v delta R A, and then the value of A here is actually the surface of the hollow, the surface of the cylinder here. So it is equal to 2 pi R, the circumference, times the L, the height of this cylinder. So you have a 2 pi RL here, and then we could calculate the value of V is mg delta R mu 2 pi RL. Okay, as I said, this is actually the idea to measure the viscosity of liquid. So now you could see that if you could measure the velocity of that object falling down, so means that you could determine what is the amount of the dynamic viscosity. Okay, or vice versa. Okay, so and then you have the mass. You could weigh this object, gravity, delta R, 2 pi, R and L is everything. You could manually get the value. You could measure that value. So means if you could measure the time or the velocity of that object falling down, you could get the value of viscosity. So and then for no slip condition, so for no slip condition, okay, I hope you could read a little bit from the textbook. So I just go faster here. So we replace the value of shear stress with the idea of this one. So it is not only not I'm sorry, tau is not anymore equal to mu du dy. Okay, for slip condition, you need to use this equation. So we substitute into the basic idea, which is weight is equal to tau A. So we substitute the value of tau, and then we could rearrange the equation to get the value of V. Okay, this is the equation to get the velocity if we take slip condition into account.